Hello, everyone. My name is Craig Knoblock. I'm a research professor in computer science here at the University of Southern California, and I'm also the executive director of the Information Sciences Institute, which is a large research lab that's part of USC. So today I'm going to tell you about some of the work we've been doing on building knowledge graphs to solve societal problems. And I'm going to bring up my slides now. Okay, so I'm going to talk about this work, as I said, on building knowledge graphs. And this is really motivated by a variety of applications that we've looked at. I'll talk about some of the applications, the challenges that arise in solving those applications, and our corresponding solution to those. And this is all part of the work out of the Center on Knowledge Graphs here at USC, which is a center that has about 40 people in it or so, including a number of students that work on various projects. Okay, so first let's start with what's a knowledge graph. So basically the knowledge graph is essentially a way of organizing a set of information. And the idea is that you want to start with some set of data that could come in from any of a variety of sources. So maybe this is information out there on the web, could be information across multiple databases, it could be in spreadsheets. And the idea is that the original information may be all disorganized, essentially disconnected, making it very difficult to query, analyze, and sort of visualize this information. And the goal of turning it into a knowledge graph is to create an organization of the data that's basically clean, organized, linked, which in turn makes it easy to do querying, analyzing it, running machine learning algorithms on it, and so on. And so I'm going to tell you how we actually do that. So just a little bit more detail first in terms of what we really mean by knowledge graph here. So the way we organize and sort of store knowledge graphs is in terms of a set of triples, right? Where each triple corresponds to some entity, right? And you have a head entity and a tail entity, and you have the relationships between them. And this slide provides a nice example of the former president of the United States, Barack Obama, where there's a set of information that's organized and stored about him. For example, that he was born in Honolulu, right, which is the capital of Hawaii. He was married to Michelle Obama. And so you can see there's a set of sort of entities that are sort of discussed or organized into this graph, and then a set of information that's about him, right? So it could also be things like that he's a male, that he has a certain birth date, and so on. And this is a very general representation. You can take information from almost any source and turn it into this sort of triple representation. And the underlying sort of way it's stored is in a language called RDF, which is essentially stores this triple representation of information. Okay, so that's the basic knowledge graph. Now I'm going to just mention a few applications, and I'll discuss these throughout my talk. So these are various applications that we worked on over the years. And I think they nicely highlight some of the uses of knowledge graphs and then bring up some of the challenges that we need to address to effectively create these types of knowledge graphs. So the first one is on fighting human trafficking. And this is one where we've worked with law enforcement agencies to help them come up with a knowledge graph that allows them to find information out there on the internet, essentially on web pages, that allows them to much more effectively locate traffickers and effectively be able to prosecute them. Second application is one we've developed in collaboration with ATF, Alcohol, Tobacco, and Firearms, where they were interested in being able to find illegal arms sales, which are usually hidden by buying and selling across different websites. And so the idea here was to be able to aggregate information across many websites and put it together, allowing them to identify these potential illegal sales. And the third application is one on forecasting cyber threats. So this is one we looked at where the idea is to actually aggregate data from a variety of different sources, including things like the dark web, news sites, blogs, as well as databases published by government agencies about various cyber threats and cyber attacks. And so I'll talk about all three of these applications throughout my talk and just use them as sort of motivation for the kinds of problems that we're solving here. Just to give you a big picture though, there's a variety of technologies involved in actually being able to create a knowledge graph. The first is, some kind of harvesting, right? The information needs to come from somewhere. This often involves aggregating data from different web pages or different websites. Maybe it involves pulling in databases or any of a variety of places to get the information. Then there's extracting information. Often this information is sort of in raw text. Sometimes it's structured information, and somehow we need to get it into a more structured format, oftentimes to work with it and analyze it and so on. So there's a lot of sort of underlying extraction capable technologies that are available to sort of apply to further structure the data. Then you have the problem of sort of bringing together information from lots of different sources. The challenge here is that the information may not be represented in the same way across these different sources. Things may be named differently. So we have to worry about sort of the terminology that's used in each website and how to align that terminology across the different sites. And so we use what's called an ontology often as sort of the glue for this, right? The ontology provides a set of terminology and structure for the data that we're going to extract. And we take each of these sites and essentially take the data and map it to this ontology. And we've built various tools for being able to do this and techniques for automating some of this. Then you have the problem, even once you've aligned it at the schema level, then you have the problem of actually integrating the data across different sites at sort of the entity level. Because what can happen is you have multiple sites that are talking about the same entities, but they refer to them in slightly different ways, or they name them in slightly different ways. And so you have this entity linking problem where you figure out if one entity in one source is the same as the entity in a different source. I'll talk about how we do that. Once you do that, then you have to have a way of efficiently deploying this knowledge graph. Meaning I need to turn it into some kind of scalable database structure that I can query. There's a variety of techniques for doing that, and I'll talk about one particular approach we've taken in some of our sites. And finally, once you have all that, you have your knowledge graph, and now you can run various kinds of querying, visualization, learning tools on top of the data. And I'm going to talk mostly about these steps 2 through 5 here in my talk. Okay, so let's start with the first application. I mentioned illegal arms sales. So the challenge here is that you essentially have hundreds of websites out there on the internet that are allowing people to buy and sell guns. Now, these by themselves are not necessarily illegal. The challenge is that sometimes what people will do is they will buy guns on one site, sell them on a different site. And it is illegal to buy and sell guns across state lines without appropriate license. And so the challenge is, how do you actually locate this information when it's spread across hundreds of different websites and new websites becoming available? So the big challenge here is being able to essentially extract automatically the data from these different sites and being able to align them across the sites. And so I'll talk about some of the initial work that we've done on this topic to address this problem. So here's an example page from one of these sites, right? So this is an ad for selling a particular gun. And you can see that there's some regular structure across the sites, and there's going to be hundreds or thousands of pages on this site that would all have the same structure. So here shown in red is the actual structure that we'd like to extract from the site. And the question is, how can we discover this kind of structure automatically? And so one of the things we've done is worked with another company called Infralink. And this is work done by Steve Minton and his team, where they would start with a set of pages. So you have some set of pages, and basically get the set of pages by essentially going to the site and spidering all the pages on the site. So you can do this and pull in many, many thousands of pages. But the challenge is that these pages may be in lots of different formats. They're not just going to be of the type of page I just showed you. They could be pages that also are sort of navigation pages, top-level pages, pages about their legal, how to contact them, and so on. And so the question is, how do you actually find the pages that you're actually looking for? So the first step is to actually organize the pages by the type of information that's on the page. And so we can essentially create a set of templates or organize the pages into a set of templates by essentially clustering them. And the way this works is you essentially look for common sequences of terms on these sites. And if they're common across all of the pages, then they're not interesting. But if there's a set of terms, sequences of terms that are common across some subset of the pages, then we can use that as a way of actually clustering these into groups of different page types. Once you have that, then we can say, all right, now we can have a set of page types, right, where all the pages are within this group, given row in this case, are of the same type. Then we can try and infer an extractor from those pages. And the idea here is to do something similar, where now we're looking at, for each of those set of pages, we can select a subset of those pages. And then what we're looking for is sequences of common terms that occur on every one of those pages, right? Because that's going to be sort of the implicit underlying structure behind the page. And the things that are actually changing on the page, that's often the content that you're looking for that you want to extract. So the idea is you can actually do this analysis on these kinds of pages automatically, find this common structure, and then use that common structure to automatically infer and extract it. And this allows you to then pull off information from these pages automatically. So this, given a tool like this, which we've built, you might come up with a result that looks something like this. So this is, each row in this table here corresponds to a different web page, right? So, and then each column is the set of information from those pages that's all in the same location on the page, right? In the same, template, essentially, right? I showed the sort of red boxes on the earlier slide. So, for example, this first column here might correspond to the actual title on the page, right? And you have each of the different columns, and there's, maybe 18 to 20 columns per page. So we have this, but this isn't the complete solution, because notice that at the top here we have some, what might be think of as names on these different columns, but these are just automatically extracted, and it's just the token that immediately preceded the piece of extracted information. So some of these do actually give you a sense of what's in this column. For example, the description, there was a token there immediately preceding the description that includes the word description in it. But really, if you think about, pulling data from, 100 of these different websites, now we have to figure out, well, which things or which columns of information are the same across the different pages, right? Because we need to find the information that's sort of common across the different sites and try to do that automatically. So let me tell you next how we do that. So the task is, we really want to come up with these, what we call the semantic types. These are essentially the labels on each column of information, right? So for this, here we have an ontology that's behind the scenes that we're using to do this labeling. And in this ontology, we have something called an offer. And an offer contains things like name, descriptions, identifier, date posted, and so on. And so what we're trying to do is look at each column and figure out, well, what does it correspond to in our domain ontology, right? So this might be the name of the offer, right? Where the name corresponds to the title. This is the description, this is the date it was posted, maybe the street address for where it's being sold, and so on. And so what we want to be able to do is to actually come up with these labels automatically. And we can do this using some machine learning techniques. So this was a technique developed by one of my PhD students named Pham, and published in a paper in the International Semantic Web Conference in 2016. And in this work, the idea is that you're going to train the system, but you're going to train the system using a set of very generic type of features. So the kind of features we use are things like Jacquard similarity, which is, how many tokens do each set of data have in common between the two? Or cosine similarity, which is often used in conjunction with TF-IDF, which is what search engines use to look at whether or not two documents are actually similar or not, or how similar they are, based on the words that they have in common and how frequent those words are. And so this just shows two different types, right? So we have Jacquard and cosine over here in this table, but really the algorithm uses at least different types of information. I just don't have room for them on this particular slide. But imagine that you have a set of generic kind of ways of comparing different columns of data. And then what we're going to do is we're going to train a machine learning classifier, right? We're going to give it several different sources of information. And this is a very, very simple source, just to fit it on the slide. But source one might be about soccer players and contain information about names and heights of players, for example. And source two is also about soccer players and only contains names. And the way the training works is that the system takes each of these pairs of columns. So we're going to compare source one and source two. We're going to compare the first column of source one to the first column of source two, and come up with a set of scores in terms of how similar they are in terms of these different metrics that I described. We do that the same thing for height and birth name. And that's going to come up with another comparison, but these ones are ones where it's not a match. And then you can feed all this into a classifier. So in this case, we used a random forest classifier to essentially train the system over a set of sources. And it comes up with, a generic classifier that can be used in this domain or in other domains. So you can actually apply it across the board. Then the idea is, once we've trained this model, then along comes a new source, right? So here I have the original source I've already trained on. I have a new source here. I'm going to compare this source against all the other trained attributes. come up with scores, and then the classifier, which has already been trained to distinguish between the true and false, is going to come up with a prediction about whether or not what this corresponds to. In this case, it's going to predict that the most likely label for this column is going to be the birthday. And so this is a very scalable technique that we can use to automatically train the system to be able to come up with these semantic labels for the data. Once we do that, now we can take a table of data I showed you before. And before I only had the sort of the heading extracted. Now we can come up with an assignment automatically. So you can see this gray row here has the actual assigned labels. And those are almost all correct, all except for the last one, which actually turned out to also correspond to the postal address, right? So it was actually the postal address. It predicted some other thing, partly because there's a lot of noise in this particular column. But in general, it's able to do quite well. If we look at our overall results on this particular types of data set, types of web pages rather, you can see that the average number of attribute sources were about 18. So in this case, we had 10 sources, and we classified about 176 attributes across those 10 sources. So the correct prediction action, meaning it got the correct answer as the first result, it was able to get 56% of the time. If we look at the top 4, which is really still quite useful because you know, it's actually we can use this in an interface that allows the user to sort of review the results and do the final labeling. It was able to get 89% accuracy, which is really quite good. And the MRR is just stands for mean reciprocal rank, is another way of scoring these things based on, you know, top 1, top 2, top 3, top 4. Okay, so that's the results in terms of this particular technique. So I want to move on and talk about the next application, which is applying sort of knowledge graphs to this work around counter human trafficking. And here, I mentioned the challenge is that we really want to help support law enforcement agencies use all the data that's on the web to help them, you know, better exploit the information that's available to find and prosecute traffickers. And in this case, we mostly used web pages. So there's essentially these web ads that are out there. And the idea is we pulled in roughly 100 million of these web ads and then put together a knowledge graph of this information that allowed them to then really understand the data and navigate the data. So here's a page from the actual application that we built for this, one where you're allowed to actually, where it allows the law enforcement agencies to search by phone number and then get very detailed information about that phone number. So for example, these are all the ads in which the phone number was used, you know, the dates that they were used on, the characteristics of the people that are being described, you know, age, ethnicity, hair color, height, weight. Over here in this part of the picture, oh, this is a map that shows the different locations where the ads were actually posted. And here we have the actual timeline in terms of when these posts appeared for the different location stuff. So you can see you get a much more detailed look, and you get a look at how these ads are actually changing over time, which really wasn't possible for them before because they could really just get a snapshot from today because they weren't aggregating this data over time. And this turned out to be quite successful. So we built an application that was deployed to something like 200 different law enforcement agencies. And several of them reported back to us that they were quite successful in being able to use these types of tools to successfully prosecute traffickers. I mean, both to find them and to prosecute traffickers. And you know, they were very pleased with the technology. But what are some of the challenges here? So here's the underlying ontology for this particular application area. And as you can see, this, this ontology, you know, has a bunch of different categories, like the web page itself, but also the offer, right? I mean, the people that are involved here, the person or organization. And one of the big challenges is trying to find, you know, who are the common entities across the different sources, right? Is this the same person or not? And so we worked on developing some entity resolution techniques called collective entity resolution. And this was developed by Linhao Zhu, who was at USC at the time. And she developed a technique for essentially looking at this entity resolution not as sort of a pairwise thing, trying to link it, but more as a collective entity resolution problem, right? Where I have a set of information about some entities. And you can see here, we're going to do this in the context of products, where you can see I have a different set of different products. And what I have is I have pricing information and manufacturing information and description information about each of these products. And you know, the actual products there's multiple different products here. And so the challenge is to figure out, well, which of these products are actually the same or not. And so you can see that in this case, you know, product 1 and product 2 are the same, and product 4 and product 5 are the same. And the question is, how does this actually work? So sort of the traditional approach to doing entity resolution like this is to do what's called pairwise comparisons, where you look at, okay, different pairs of information, try and decide which pairs are actually the same entity. But this is really challenging because you look here and you see, well, in some cases I have missing prices, other cases I have multiple prices, and I've got to come up with sort of different distance metrics to decide how good a given metric is. So this is quite challenging. And so the idea behind this approach is essentially treat this as a graph summarization problem, where I'm going to essentially try to group things by the graph. So I'm essentially have some similarity metric that analyzes how similar any two nodes are. And it can be applied essentially on the same node types and decide which of these to group together. And so it might create these what we call sort of super nodes that look like this, where I say, oh, okay, it looks like maybe product 1 and product 2 are the same, and these descriptions are the same, and it sort of does this initial grouping. And once we have this initial grouping, then we can, that we call super nodes, they can then also create the super links, right? These are sort of the common links between these super nodes, right? And we can then use these super links to help us figure out, well, you know, which of these groups are likely connected to which other ones. And one of the things you can do here is to sort of do an iterative refinement over these graphs to come up with better and better graphs to represent the underlying set of data. So if we take a particular subset of this, so I'll just take this little subset of the overall graph, and I can expand it out. And I look at this and I say, all right, I have these super links. And what the super links in this graph are telling me is that it really would correspond to all of these different links here between the individual nodes. And if we reorganize things a little bit, so if we take this middle node here and say, well, maybe what if we broke that down? Then you could see that you get actually a better match in terms of, you know, which links are predicted from the underlying data sources. And so by separating up these things, then product 3 is linked to Bosch, and product 4 and 5 are linked to Bose. And this, in fact, is actually a better sort of grouping of different entities. This technique worked quite well. So you can see this is compared to a number of different systems. The system that was developed here is called COSUM. There are 2 versions of it, COSUM B and COSUM P, just using different metrics in terms of, you know, how they were doing those the linking. And the highlighted boxes correspond to the best results. And so you can see, and it's comparing 3 different domains: author, paper, and product, precision, recall, and F measure, and almost across the board, COSUM P performing other systems. The last application I'm going to briefly mention is on forecasting cyber threats. And here the goal is to essentially be able to automatically forecast these cyber attacks by using sort of the underlying data in the system. I mean, different underlying sort of data sources are available on this. And one in particular is quite informative, which is the dark web. So there was all this information on the dark web with people posting potential exploits, people posting discussions of different potential cyber attacks and so on. And so the goal here then is to build a knowledge graph of all this relevant data and then leverage machine learning, text mining, and sort of behavioral modeling techniques to be able to predict these types of attacks. And one of the challenges is related to the knowledge graph part of it, which is how do you actually provide efficient access to this very large amount of available data and support real-time query? So I'll tell you briefly how we did that, which is we basically pull in all the data from all these different sources I mentioned, right? So this includes things like social media with Twitter, conference websites, blogs, these dark web forums. We put all this information together and map it to the domain ontology. So in this case, we use a tool called Karma to do this mapping. And then finally store the data in Elasticsearch. The domain ontology looks like this, which is, you know, we have things like exploits and vulnerabilities, and we have blogs and posts. And the idea is all the information from these different sources gets mapped to this common ontology. And then one of the interfaces for the system is this cyber knowledge graph dashboard, where I can then query based on these different types of things. So I can query based on vulnerabilities, and I can put in keywords, and I can get back some set of results and for the results. So the question is, how do we create this and organize this information? So we store this information in a system called Elasticsearch, which is an open source tool that's really quite nice. The information is organized in this triple representation I mentioned earlier, which we stored in a language called JSON-LD. And essentially what Elasticsearch is essentially a document store. And so what we do is we create a set of documents that actually capture the information from these different sources. And because it's a document store and it's built on top of Apache Lucene, it's very efficient. It supports horizontal scaling, replication, load balancing, and you can do very fast queries. And really the secret behind why it's so fast is what you're really doing is actually pre-computing the joins on the data. And by pre-computing the joins on the data, storing them as documents, then we can get very fast lookup on this information. So here's sort of the data model that we use. So we have essentially different views of the data, right? So we have one view for malware where we say, well, this is what we might want to know about malware. And we put together information from the domain ontology that sort of organizes the data in a way that we can very efficiently query for malware. Then we do the same thing for exploits, vulnerabilities, posts, social media, so that you can essentially query for each of these things very quickly and very efficiently because you have documents that correspond. It increases the amount of storage required since you're making multiple copies of the data, but it makes query access very fast. So this gives you a sign for, in terms of a sense of the actual performance. So what you can see here is that we have the index time for about 16 million documents is about 2.5 hours. So that's how long it took us to actually, index all this information in Elasticsearch. But now if you look at the query time, so we can do keyword searches in 8 milliseconds, finding a specific CVE, which is an explicit vulnerability, at 14 milliseconds, all the mentions of a particular Microsoft bulletin, 48 milliseconds. And you get into more complicated sort of queries where you're filtering on things and stuff. It increases the time slightly, but it's still under a second. Even the most complicated ones involving aggregating and doing counts is still under half a second, right? 409 milliseconds. So that sort of brings me to the end, where I just want to summarize. So essentially, I've described work on knowledge graphs that allow us to provide this general technology that can be used for a whole range of different problems in society. You can solve sort of some of these hard problems. The research in our group really looks to identify sort of these interesting problems and address them. We like to work on real world problems. And then as each problem comes along, we essentially expand these technologies to figure out, okay, what are the specific challenges that arise here and how do we address those? And so I talked about 3 use cases in this talk. One first is, how do we do large scale web abstraction? I described techniques from like structuring and source modeling. Linking entities across sources, I described this collective entity resolution technique. And then how do we efficiently query large graphs? And describe this method for organizing the data into documents. We're currently working on other knowledge graphs. This includes the knowledge graph that extracted data from papers on COVID-19, which is clearly a very relevant topic today. We recently built another knowledge graph of satellites, where we're interested in identifying satellites that are potential threats. And finally, we have a current project where we're looking at building a knowledge graph of US businesses that are essentially built from web pages over time. And so then you can see how markets are changing over time. We can evaluate business plans, do a variety of things. So thank you very much for attending my talk today.